In this video, I'm going to talk about some common convergence issues, namely numerical roundoff errors and hourglassing mode. Numerical roundoff errors exist in all computer programs. When it is connected to an unconstrained degree of freedom, it often leads to divergence in finite element simulations. And the remedy to correct this error is to simply constrain your finite element model as realistically as possible, as if you were doing a physical experiment. Taken, for example, an uniaxial tensile test. On paper, I would draw it like this, just a rectangle with applied forces on both directions. While in the lab, this is the minimum drawing they would show to a technician. So try to spot the differences in terms of boundary conditions between the left figure and the right one, and see why real experimentalists would prefer the one on the right. Bear in mind that even though you are running a numerical simulation, it is in fact actually closer to a real physical experiment than to a theoretical drawing. That may surprise you. A second type of convergence issue that I would talk about is hourglassing mode. Hourglassing mode is a result of reduced integration. So I need to first talk about reduced integration. Taken, for example, this cantilever beam subject to end moment. It would deform into something like this. If I look closer at each segment of the beam, under the thin beam or cylinder beam theory or Euler Bernoulli beam theory, this midsection would look like this. Basically, what was normal to the midsection or neutral axis remains normal to the neutral axis after the deformation. This is the key assumption in Euler Bernoulli beam theory, sometimes called the Kirchhoff-Love assumption. However, if I were to model this problem with some solid elements, linear first-order solid elements, for instance, it would deform into a shape like this. Because these elements are linear, so the edges of this element remain straight after the deformation, which means that if I were to look at the cross-section, what was normal to the neutral axis would not remain normal after deformation. What this creates is some fictitious transverse shear in the energy of this element, which means that we have an overestimation of the strain energy after deformation, and this translates to element being too stiff. This is often called shear locking. And one popular remedy to correct this shear locking or to remove this fictitious transverse shear is to use reduced integration. Now, for example, I have my linear element with 4-node standard full Gauss integration. If I were to use a reduced integration, then I only integrate in the centroid of this element. Now look at this figure. I have negative shear on the right and positive shear on the left. Through interpolation, it would result a zero shear, transverse shear in the centroid of this element, and thereby, when I integrate it, the transverse shear contribution to the strain energy of the element would naturally disappear. However, this remedy does come with a price. If, for instance, I deform the element into such a shape, then I would get exactly the same energy as the top figure. And this also applies to this case. So all three of these deformations would end up having the same amount of strain energy, even though I'm applying obviously different deformation to this element. These are called hourglassing mode. They are modes that have zero energy and they are extremely unstable. Once they appear in a finite element simulation, they often lead to non-convergence. Unfortunately, this type of integration is usually the default setting for many commercial software. Be aware of this problem and check if your problem really needs reduced integration or not. Try to avoid using them unless really necessary.